right, our next speaker is Jean-Christophe Mifsud.
Good afternoon, everyone. So I'm Jean-Christophe Mifsud, working with Ellona. So we're all working here to provide reliable environmental data with a high spatial and temporal resolution, and to try to make the invisible visible. You can see that a little bit everywhere. I believe we are all working as well to try to have smart data to make them actionable. But is it really how we, as men and women, assess our environments? Is it really how we commit ourselves to the environments we are in as citizens or co-workers? I believe we assess our environments through our human senses. Odors, noise, allergens, health status. This is how we are in the environments we are living in. And so what we're trying to do at Ellona is to provide a combination through IoT device, low-cost sensors, measuring gas, particles, and different vibrations, liquid. We are trying also to provide odor data bank, allergens data bank, sound data bank, to be able to build up a context and understand the situation. And therefore, today what I'm going to present is how some community use our devices to be able not only to measure the H2S, mercaptan, the ammonia, the COs, and so on, but also to be able to have an objective measurements of perceptions by associating miniaturized sensors, what we call monovariate sensors, the H2S, the ammonia, and multivariate sensors like the PID or metal oxide sensors or FFT microphones. Because to conclude on this part is that basically providing, let's say, a 100 decibel on your dashboard without knowing if it's a Harley-Davidson, a car crash, a sledgehammer, or a gunshot, the remediation is going to be totally different. And that's the use case I'm going to present today. So this is a city in the Baltic country on the seaside with a whole lot of different petrochemical company called Ventspils. And there's quite a bit of citizen complaint about the smell, the odors, and what's coming from those different tankers and different situation there. So the seaport, as you can see, has different dockers, different operators, and I don't see the timer here, but I go on. And there, what you can see is that there is a very strong Baltic Sea wind coming from the north to the south, and this city is in the southern part. And of course, when there is any type of emission, when one of the operators is not as cautious as it should be, the whole city smells kerosene. Where is it coming from? Well, it comes from those guys. However, which one? How can I identify the source? And therefore, what they have set up is a standards based on odor units. In Europe, there is a standards called the EN 13725, and in the United States is the ASTM 679. This is based on dynamic olfactometry, where human beings are going to sniff different bags at different dilution and provide an odor units. And the standards in this particular case was set up at 5 odor units at the fence line. So how can we measure online with 5 odor units, knowing that there is quite a bit of storage, reception, infrastructure all around the place? So who is at stake? So therefore, as you can see, there are a lot of different sources: diesel fuel, naphtha, black fuel, kerosene, solvents coming from all different parts of the world, or transformed and stored on site. So basically what we did is to create a network of 9 different IoT low-cost sensors with different type of miniaturized MOS sensors as well, all around the sites. And you can see that there are 3 operators that, of course, usually when there is a complaint, say, it's not me. So what we did is basically trying to do a survey, analyzing the topography, of course, the main wind direction, setting up a network all around the plants with 9 so-called IOMS or electronic nodes with different meteorological stations. And this is where we begin to analyze the smell. So as you can see, we begin to have an array with different monovariate data, H2S, mercaptan, ammonia, and multivariate data, MOS sensors, PID sensors, to fingerprint basically the profile. How can we profile with fingerprint? Well, basically, we are going to analyze the different emission with the help of a dynamic olfactometry. So we set up a network, and from there, we go to dynamic olfactometry. For the ones that are not familiar, you have 4 different type of devices where you can sniff the different Tedlar bag that are samples, or canisters, but mostly Tedlar bag, that are sampled at the site. And from there, you're going to dilute with clean air those different Tedlar bag. And you're going to follow the same procedure at the dynamic olfactometry level and at the IOMS level on site. And so this is the devices, this is the training, this is the, that's not it. So this is the setup. So you collect the data in the cloud where you basically try to correlate the olfactometry data with the IoT device data. So this is a training. You see the Tedlar bag on the ground. You see a dilution system right in front of a Tedlar bag. You can see the ball of clean air. And we begin to dilute with different Tedlar bag having different type of smell or VOC. Venezuela type of black fuel, Saudi Arabia, naphtha, and we begin to analyze it. The whole process took around 5 days with 42 different origins of black fuel or petrochemical product. And as you can see on the right-hand side, you have a different dilutions with following the procedure of the ASTM 679. So on one side, we have the olfactometry. On the other side, you have the analytical measurements. And from there, you begin to build up a regression curve using PLS, partial least square regression. And of course, do not expect a fantastic R2 because it's a correlation with sensory technique as being a primary technique. And in this case, we have an R2 of 0.89, which is relatively acceptable. The minimum you can accept in this type of correlation with odor is around 0.8. From there, as you can see, we have different R2 for the different type of electronic nose. As you can see, the bottom one, the last one, has only an R2 of 0.58. Therefore, we had to redo the training with a sensory panel for that particular one. And from there, so once again, you do the sample, you send the sample to the sensory panel for the sniffing, the same samples are diluted at the IOMS, you build up the calibration curve, and you cross-check the data with unknown samples. What is really nice on this one is the outcome. What you see is 4 different electronic nose or IOMS device that are overlapped on top of each other. What you see on the y-axis is the odor units. First of all, you can see that every one of them are sensitive to a level which is below 5 odor units. For example, in this particular room right now, we are above 5 odor units. So that means it's extremely diluted. So there is some sensitivity, and chiefly there is some reproducibility. But what's really nice as well is that you can see that for the different naphtha, the naphtha from Canada, the naphtha from Kuwait, the kerosene or the benzene, the profile of the odor units are different from one another. That gives us the possibility not only to do odor intensity, but also after setting up the network, as you can see on street light or different type of urban furnitures, to set up a qualitative fingerprint. This is called a PCA, a principal components analysis, for the ones that are not familiar with multivariate statistics. Basically, you clusterize those different sampling points during the training, and you try to basically use it as a training map. On top of it, you're going to project the unknown sample, first for the validation of a model, and then for the online analysis. So that means every 10 seconds, you take the profile and send it onto the data bank. What you can see here is that the kerosene from Algeria, that is very sulfury, is very much on the right-hand side of the map, and it's extremely easy to analyze. When the other one, you can see the naphtha from Kuwait, which is relatively well identified. For the other one, you have some overlap, but it's pretty rare to have simultaneously different tanker having gas oil from Venezuela and a naphtha from Canada. So basically, the city of Ventspils now is using this online to be able to identify where the problem is coming from and find the operation. The fine today is 60,000 euros, so it's about $60,000 per alarms. So this is the dashboards of the city, and so they can have not only the different weather informations, the different gas information, H2S, and the different alkanes, but also the odor intensity. So that's what the system is able to do, because at the end, you need to act, and not only to fine. And therefore, what they did is to change the traffic light algorithm of a city online, depending on the type of odors profile that they get and the type of pollution. So all the traffic around the city is online modified. They slow down the traffic upstream, fluidify downstream to avoid the contaminations of the area. This is what I wanted to share with you. Thanks very much.
Thank you. Our next speaker is Pami Mukherjee from